Okay, so this is the first lecture. So I try to make it as elementary as possible. If you have any question, please ask me. If it's anything which confuse you, must be something wrong with my lecture. So because everything should be so standard. So my main object of my lecture is about elliptic curve. So for simplicity today, I'll only talk elliptic curve of a rational number. So it will given by a Weierstrass equation. And you want to have a discriminant non-vanishing. So we care about the group of rational points. So it is a group. As usual, you probably, in any first book of elliptic curve, you will have the group law defined by lines. You have a P, Q, R. So you get this one, S here. The P plus Q equals S. It was noticed by Poincaré that if your P and Q both are rational, the sum will be rational, so this will become a group. It was conjectured by Poincaré that the group of rational points is finitely generated. So this is actually the theorem proved by Mordell in the 1920s. Finite group. So write G over Q over torsion. So this is the Mordell Weil theorem. And the over rational number is actually completely due to Mordell. And the EQ part of tau part is actually not very big. And this one by a theorem Barry measure, I guess is less than 16 or less equal than 16, I forget. And then the R part is not really, we don't know how big the R part is, but there is the Fox conjecture that R equals 0 for 50% of elliptic curve. And but you have to order it by some way. The original conjecture is ordered by conductor, but you also can order by height, right? So with certain order. And R equals 1 is for another 50%. So it's a remarkable theorem recently proved by Manju Bhargava a few years ago, and recently for rank 0, and recently by Bhargava, Skinner, and Wu Zhang. This actually is true for R equals 0. So at least, for at least, I guess at least maybe 30% of E, and R equals 1 for at least 60% of E. I don't know what exactly this number is, but anyway, it's a pretty big positive. R equals 1. Second line, 0 or 1.
Yeah, instead of saying R equals 1.
R equals 1.
I think you should say R equals 0.
Oh, no. That's right. This is a bit confused. 30% divided by 2 is 15% maybe. Maybe 40%. This is much less, I guess. Like 15, at least this one. You have to divide by 2 for both of them. Okay, so that's a very remarkable work. But one thing you find that in particular for r equals 1 is at least 30%. So the one question we ask is that, how can you construct such a point there? So this is probably one of my purpose of my lecture. The question will be how to construct points in E of Q. Right. I can make this more precise. And this took, I guess, like last 60 years from Hingener, Fulton's wires, until Zagier. Probably the best result in number theory, the best work in number theory always have something to do with this question, how to construct rational points of the elliptic curve. So I will start with the work of the Fultons and the wires. So instead of construct these points, you also want to construct. You give x as a variety. You probably want to construct the points from E of x. This is the home from x to E. If you fix one point here, say P here, so it's a market point, then I can make a requirement to put some 0 here. So I want P map to 0. Right. You can ask this question. Then this will be a group. According to Fultons, if I write 0 here, I just make P to 0. Then E0 of x, if you tensor ZP of Z, is basically isomorphic to the home of P is a prime, the TP of E, TP of the Jacobian of x. And this one, this is attached module I'm going to explain later. This is homomorphism and compatible with the Galois group, Q bar of Q. So this is a remarkable work. This is a work for a variety of high dimension. The existence of x points is equivalent to some statement about the Galois group. This is why the Galois representation is very important in arithmetic geometry. Right? This is the Taylor's conjecture. This is the Taylor's conjecture. And proved by Fultons in 1983. Okay, so now we want to specialize this x be a modular curve. Of the P1 over Q. So this gamma is in the SR2Z, something called a congruent subgroup. Then this x will defined. X will define x is this one is just the Riemann surface, right? The Riemann surface. And once this thing, x has a model, has a canonical model. So define over certain Q. I write gamma here. It's a finite. It's a number field inside maximum abelian extension of Q. So nevertheless, I still concede. x as a curve over. So this is called absolutely connected. This one spec of Q. So I still consider x as a curve over Q, but it's not absolutely connected. So we can apply this Fulton's theorem to this modular curve. And I make some requirement because I have this one is a cusp. But this cusp may not be necessarily defined over rational number. But they are, you can require the following. So I can require the E0 of x, maybe a tensor Q. At least I can define this model be home of 0 of x of E tensor Q, but I require the cusp goes to a torsion point. Then you apply the Fulton theorem, you will get E0 of x, that's a QL or QP. Up here is isomorphic to the homomorphism of VP of E and the VP of Jacobian of x. That's the Galois group. Okay. Now is the next very important theorem, major theorem by. So this is not 0. This is by something called modularity. Wires tell us. Or Taylor wires. And many, and completed by Conrad, I try to remember Broglie, Conrad, Diamond, Taylor, right again? Okay. So this is like in the 1995 to 2000, I don't know. So this next major result. The two major results combined together just tell you that, well, even I don't know, my elliptic curve with rational points at least has a modular curve point. Right. So this is why I say that. So there's a question to construct a rational point of elliptic curve is really accumulate the most important result in number theory in the last 30 years. Okay, now I come to some idea about Hingener. Okay, so after Fultons and wires, we know that any elliptic curve will be parameterized by a modular curve. Now the question is if you want to construct a point, an elliptic curve, maybe it's sufficient to construct a point, a modular curve, right? So that's the Hingener's idea. I will come back to Hingener how he exactly worked on this thing. So he fixed, so the fix K imaginary quadratic field is D is less than 0. We suppose this one is embedded the complex number. So then what's going on that instead of consider this upper plane, you can replace upper plane by this K over gamma. Right, so these are called CM points. In the plane. So they're imaginary quadratic points. This one is inside of this X. And priority is inside X of C. So in fact, it's inside XK of AB. So this is by the CM theory. Okay. So if you fix a point, so let F be a homomorphism from X to E, so something called a modular parametrization, I can continue this picture there to E of KAB. So I got many points on EKB, and all the image of these points, maybe I should call it Hingham points. Here I call it CM points. You can do much better in the sense that this one has action by a Galois group of KAB of K. So, I mean, you can show that there's a set is stable and there's an action. So the image of these points is basically it's a Galois module of the Hingham points. So in this case, I want to do something slightly better. By taking a character, so I started that chi be a character from Galois KB over K to complex number. So this is a finite character. Then I can fix one point here. So to fix this one, let's fix a P inside, of the CM of gamma. I fix F inside X of E of X, 0 here. Then I can see it. I use the notation purposely make you confused with this P and this P. And this P will be referred to as the periods. F of gamma here defined to be integration of Galois KB of K of F of P of sigma chi sigma d sigma. Well, I mean, I just write in a very fancy way that I can do maybe slightly better. So this is actually, this is really a finite sum, by 1 over d, whatever. Some finite sum, if I write it. The F and sigma inside Galois of L of K, right? If you want to write on this way, is F P of sigma, chi of sigma. So this D will be, L will be K joined with P, D probably a bit more than that. Doesn't matter. So L is certain. L is some field in the KAB, number field inside the K. It's a Galois there, and the D is the degree L of K. So I write in this very fancy integration because I want to make a comparison with the lecture I'm giving tomorrow, but in fact it's really a finite sum. It's not that scary.
Could you write the name of that point? You said you were going to refer to it by a certain phrase.
This point?
Yeah, you called it something.
Periods. Periods integral.
Okay.
Okay, so this is the point inside E KAB tensor with C. So the question, the main concern of this thing is that when is the P of chi not zero? So we construct a point there. We want to see when this is non-zero. Okay, now I want to talk about the origin of this construction. All this construction and the famous problem, the Gauss class number one problem, is written in a bizarre paper of Hingener in 1952. There's a Hingener 1952. So in one single paper, he solved the Gauss class number one problem, also giving infinitely many examples of the prime congruent number. So this is why I can describe his work. So there, he introduced this kind of points. Of course, in the Hingener's time, he cannot study general elliptic curve. There's no modularity. So he only studied very special elliptic curve. He knows it is modular. And so that's a modular curve he studied. It's E y squared SQ minus X. So that's a curve he studied. This actually has a Cm by Q of I. So the conductor of this curve is 32. And he didn't know all this then. Anyway, he constructed an explicit morphism from X of 8 to E. This day we can do better. We can say X0 of 32. But he constructed an explicit map from X8 to E by computing all these modular elliptic functions. And not only that, he also take n be a prime, be either a prime P is congruent to 5, 7 mod 8, or 2P congruent to 6 mod 8. And he can see this K equal Q square root of negative n. And he construct this in. Also, he construct a special points, some special points, Cm points. P inside Cm, this gamma D2. And he basically study, and his basic theorem is the following. He proved the following very remarkable theorem. He proved that. So in the terminology I write down, the P, F. So this is the trivial character. Chi 0, the trivial character. He showed that the theorem. He proved that this one is not 0. He basically consider point, show them non-zero by certain miracle method. But we're not going to describe that. What? Yes. And consequently, he proved the following. So the consequence is the following. I mean, the reason he proved that because you see this P of f of chi 0 is basically inside E of k. E of k is basically is almost like E of q, and the direct sum En of q. En of q is the elliptic curve of ny squared equals xq minus x. So the consequence, because this one is more or less trivial, E of q has only have torsion points. You don't have non-torsion points. So consequently, so the rank En of q is bigger than 0. Right. So that's basically what Hingener proved. It. He proved for fixed elliptic curve that infinite many quadratic twist has a positive rank. And then this elliptic curve is not an arbitrary one. Well, it's a very simple one, but it has a very long history. So this elliptic curve is the one studied by probably by much earlier time of the congruent number problem. So equivalently, that so this n is a congruent number. So this, by definition, means that it is the area of a Pythagorean triangle. I can write the triangle precisely, so you can have diagram here. Pythagorean triangle means that you want to find a right-angled triangle with 3 sides, a rational number. The area is n. But if this elliptic curve has a solution, then you can construct this triangle very easily. You get this one area, so x squared minus 1 divided by y. Another one is 2x divided by y. This one x squared plus 1 divided by y. That's basically the right triangle you can construct from the solution of elliptic curve. Okay, so if you have a chance to look at the Hingener's paper, that's a very interesting one. In the first 4 pages, he just described the congruent number problem. Then he trying to construct a solution. In the middle of the page, suddenly he switched the congruent class number 1 problem. He claimed that he solved the class number 1 problem. That's a very remarkable paper. As we know, Hingener is not a professional. He's not a professor, university professor. He's probably a teacher in Gimani's, right? It's like a high school, whatever. And this is a paper he wrote when he was 59 years old. And it's remarkable that he can manage this complex multiplication and using this today a pretty modern idea to solve diophonic equation. So Sayre sometimes says that the modularity of elliptic curve really goes back to Hingener. So he's really the first person to use the modularity of elliptic curve to solve a diophonic problem. Non-torsion, yeah, it means a non-torsion. My period already turns to C, so it's okay. Yeah. Hingener work at the very beginning, people believe Hingener work has some gap, and it took, I guess, 18 years. How many years? 68. In 1968, people start to believe what he has done is correct. But that's already, sadly, he already died 4 years early, before he knows his work was recognized by community. Okay, now finally, I want to talk about the Zagier formula. So there is some assumption which Birch called Hingham condition, but Hingham never used this condition. So it's called Hingham condition by Birch. Hingham-Birch condition, Hingham condition, called by Birch. For people who are interested in the history of this Zagier formula, you will see one book. It's edited by me and Henry Dalmon. That's for the MSRI workshop in 2001, where we go through all these historical part. So in this assumption, so first of all, you want x. I don't want to concede x naught of n. We only consider this kind of elliptic curve. This n is the conductor of E. And is the first assumption. Second one, I wanted the D. The D will be this k. Remember, this k is equals q, square root of d. I want the d to be order and congruent to n. The last part, and also we require that any p divided n implies p split in k. So the last part, we want chi. We only consider chi will be unramified. So this is this condition called the Hingham condition, where this is just assumption which grows, and Zagier took. Only 10 o'clock. Is there any question? So these conditions has two consequences. Well, so then the theorem proved that. Let me write on two parts. The first part is that if this Pf of chi is non-zero, if and only if that certain special value of error function is vanishing. So I need to explain a little bit of that. So this error f, oh, I didn't write it. Yeah, it doesn't matter. This f, let me write E here, probably is better. Actually, it's the same thing. So this LE chi S is a Rankin Seiberg convolution of two error function, LES and L chi S. So it's a degree 4 error function because the chi, it's a character. So if you write it very precisely, it's like so it's like LE chi S. If LE S is summation and to S power, and this one we write on will be summation A, you normalize by idea. Idea, norm is idea. That's chi of S. So this is the idea inside O of K, something like that. Probably needed to normalize by some fact. And the Hingman condition, let me write down these remarks. This is not part of the theorem. I just explained that. The Hingman condition implies that this L, LE of chi of S has an order functional equation. So first of all, priori this one is holomorphic, is a holomorphic continuation to whole complex plane. And it satisfies certain functional equation. The Hingman condition basically implies that this one will have order functional equation will be, if I complete this in by some gamma function, then this is almost like equal to negative LE chi 2 minus S. So in particular, LE chi 1 equals 0. So the derivative is the first number you want to concede. The Zagier theorem says that this Peirce integral is non-vanishing if and only if that the derivative of L function non-vanishing. Okay. Oh yeah, one thing I get confused. I forget to say that I didn't define this one precisely. Let me write it down. Sorry. This is the one. Second part is P f chi is defined using a canonic CM points. So the CM point is on x naught of n, and then this x naught of n, so it's in fact what's going on. This x naught of n, first of all, by have a modular interpretation. Probably in the next lecture you can see that. It is given by this one is a pair matrix is equal to all the pair matrix E1 to E2 of phi, kernel of phi is isomorphic to Z mod and Z cyclic group. So the CM points you can choose is the canonical one. So this P I will choose will be C, take O of K, map to C of some idea, right? Inverse. This is idea, such that O of K mod N is a sum of the Z of NZ. The existence of this of n is also guaranteed by the Hingman condition. The Hingman condition have two consequences. One consequence about the L function, one consequence of Hingman point. Okay, so this is one theorem of Zagier, but in fact they prove much more than these. So the Zagier formula is, so maybe I write it down, is the following. So if you can see it, is the P f of chi, P f of chi, the narrowed Heidelbergian. This is a narrowed Heidelbergian. This is equal to this is called an h of k. This is a class number. This is a half of units there, divided by 8 pi square of the Peterson product. This is the one you can have. Let me write down the degree of f. No, that's probably, it doesn't matter. So let me try just write it there. F and f times L prime of f chi 1. So this is a degree of f. Remember that f is a morphism from x naught of n to e. So in this way, you have a degree of f there. You divide by degree. This is essentially the theorem of Zagier. I guess I finished everything I want to say on the talk, unless you have some question.
Could you say what the u is in the numerator?
Oh, u is the units. Okay, cross.